controller synthesis techniques for infinite state systems. And so some of the examiners have joined online. So we have Professor Srivatsan from Chennai Mathematical Institute and Professor Reina Dimitrova from CISPA, which is in Saarbrücken in Germany. And I think Raghavan will also be joining online. Yes, and welcome to all of you all, and over to you, Sandra.
Hello. 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 Yeah. So, good morning, everyone. I'm Stanley Samuel, and I'll be talking about my PhD work, controller synthesis techniques for infinite-state reactive systems. This is work with Professor Raghavan and Professor Deepak from IISc, as well as in the second part of the thesis. It's in collaboration with my collaborators from the Max Planck Institute for Software Systems in Germany. So, reactive systems are everywhere. For example, a prime example of a reactive system is Amazon warehouse robots. For example, if you make an order on Amazon, the order might be placed in some warehouse at some location. Robots would pick the order from one location and deliver it to another. The goal of this robot would be to, say, avoid some obstacles. Another example is if you have liquid spills on the floor, the robot may not be, used to handling it. And more specifically, Amazon mentions that for these robots to work, humans must be and everything must be clean. So there are certain requirements on these kind of systems. Now, they're reactive in the sense that they continually react with their environment. For example, this robot can sense through GPS which location it is in the 2D plane, and then make a decision accordingly in which direction to move. However, design and implementation of such reactive systems are non-trivial and error-prone. For example, in the warehouse itself, a robot just punctured a can of aerosol and injured a lot of a dozen members of the company. And this gets worse, as I said, if there's a robot moving on the floor and there's some spill, it's not really accounted for. So what does the robot do in such situations? Of course, another infamous example is that of Boeing in the MCAS software system. What Boeing did was, because of the change in the airplane design, the airplane was going at an angle above safety limits, and Boeing installed some software without actually telling the pilots. And what the software did was, as the angle increased beyond a certain limit, the software automatically got the plane down. Now, the problem was that the software was too powerful. The software, of course, could control the lever that the pilot was handling. So when the pilot is pulling up, the software pulls it down. And it was so powerful that the pilot could not even pull it back up. So this is an example of a safety critical system where any error in software can cause a lot of damage, and especially in terms of loss of lives, in terms of financial loss, or in terms of reputation to the company. However, these reactive systems are still designed in the traditional software engineering practice. For example, and it works, by the way. For example, you have a set of requirements that the system should satisfy. There are a team that designs it, then somebody implements it, and then you write test cases for this implementation to verify if this system is correct. For example, in the aerospace domain, a typical system could easily have up to 84,000 requirements. And for each requirement, you would have a test case that is written manually. Of course, this is not really trivial. And this is where a lot of bugs can creep in, a lot of test cases can go missing. And since test cases are not exhaustive, formal methods come to the rescue. Of course, formal methods is essentially using math in very layman terms to prove or guarantees about systems or ensure how your software is reliable. And a branch of formal methods is synthesis, which is also known as the holy grail of software engineering. The synthesis question asks that, given, it asks whether we can synthesize the controller software automatically, right, which is correct by construction, with respect to the specification or the requirements given directly, right? So we're talking about no human intervention, right? Of course, when I say no human intervention, I mean from the requirement to the implementation process. There's no human intervention, but the human is still required to write correct specifications and requirements. So this is where this brings us to infinite state reactive synthesis, which is also known as control synthesis for infinite state reactive systems, which was first posed by Alonzo Church in 1957. And what this problem talks about is, given a reactive system model, which is possibly infinite state. Right? If you consider the Amazon robot example, it would be infinite state because the 2D plane on which it is moving, the variables could range over, say, reals. Right? Now, given such a reactive system model, somehow, let's not get into the details of how it's modeled, and a specification. Let's say a specification is to reach destination while avoiding obstacles. The goal is to synthesize a controller which is correct by construction. What correct by construction means is that all behaviors of this combined system, think of the controller being plugged into the robot, right? This combined system, when it's continually interacting with the environment, all behaviors satisfy the specification. That is, it's never the case that, say, the robot goes and hits a wall or some obstacle. And while it should satisfy reaching the given destination. Now, from 1957 to early 2000, this area was largely of theoretical interest because of the challenges faced, right? For example, this problem is highly interactable, especially when you have finite state spaces, but very large states, right? State space. The complexity can easily be doubly exponential in nature. And it's easily undecidable if you have an infinite state space. When we started this problem in around 2017, there were a lot of challenges. Infinite state reactive synthesis was a very, very nascent field, right? And back then, very few or none, to the best of our knowledge, even spoke about infinite state reactive synthesis in this specific context. There were also approaches which were unsound. And a reactive synthesis back then majorly handled finite state reactive synthesis. For example, if you want to synthesize a bus arbiter from a given specification, this is an arbiter in the hardware which grants, say, access to the bus, right, for to multiple CPUs. One property that you would want is the bus is granted to at most one CPU at a given time, which is a mutual exclusivity constraint. And you could have a conjunction of such requirements as a specification. And there were a lot of tools in that, or dealing with the finite state synthesis, such as Bose, Acacia, that could really handle industrial standard or industrial case studies of controllers, right? And they actually synthesize the full bus arbiter. However, standard, where the common standard we should be using, although in finite state setting you had SynCom, which was a standard competition. It is not clear how to go about modeling this problem, and tackling undecidability is another challenge, which is a problem in itself. In 2025, by now, this thesis explores some initial efforts in solving the infinite state reactive synthesis problem. Apart from this thesis, there is an initial effort going on to standardize benchmarks using a common specification format, and more. Of course, there are more tools and interesting techniques available in this domain. So now that you have understood the context of this field, the core contributions of this thesis as follows. One is a framework for modeling the infinite state reactive synthesis problem. And second is synthesizing controllers for this problem, which has some properties. First property that we're interested in is correct by construction, which I just explained. That's by definition of the problem. Second is scalability, right? Can we synthesize these controllers as fast as possible, and so that this is feasible for real world examples. And third is the notion of resilience to unexpected disturbances. Recollect that I mentioned that the Amazon robot is designed to only work when there are no liquid spills or no obstacles in between. But what if there's a liquid spill? What if something just comes up and the robot is not really taken care of, is not really prepared to handle such situations? So in such situations, can we give a best effort solution or the most resilient solution to that problem? And that's what we'll be seeing in the second part of the thesis. So coming back to the infinite state reactive synthesis problem that we now know, a common way of modeling this problem is using two-player games. What one could do is you can model this interaction between the system and the environment the ongoing interaction as a two-player game. Right? You could think of the game as the game played between the controller and the environment, and the controller wants to win the game against any move of the environment. The environment could throw at you some spills. The environment could be a tornado, could be anything. But how can you still satisfy the objective while against any move of such an environment? Now, if you solve this game, you get a strategy for the controller, which corresponds to the solution of this infinite state reactor synthesis problem. And from now on, till the end of the talk, we'll be only talking about games and strategies that will be used to solve this infinite state reactor synthesis problem. So I hope everything is clear so far and the setting is motivated well enough. With this, we move on to the first part of this thesis, which is infinite state reactor synthesis using a kind of games that we call logical LTL games. And in this work, we start with a simple motivating example, which is an elevator. Let's talk about a simple elevator where you could have the system or the controller, which is an n-floor elevator, right? We are keeping it bounded for simplicity, or this state space could be infinite in general. And the elevator can move up, down, or stay in the same location. We want to synthesize an elevator controller that ensures that you can satisfy one of these properties. One property that we'll be interested in is the elevator always stays within n floors. The other property is that every floor is visited infinitely often. It's simple in the sense that we are not assuming any arbitrary input by the user. Of course, you could have more complex scenarios. Now, logical LTL games, it's a game played between two players, the controller and the environment. And the game consists of a finite set of variables V. In the case of the elevator, you denote this set by a single variable x, where x is the value of the current floor. Right? The value of x is talks about the current floor, and let x range over integers, let's say. So the rules of the game, or the allowable moves of these players, are represented by two predicates, con vv prime and n vv prime, which is x prime in the context of an elevator. We have as you mentioned, the controller can move up, down, or stay, and the environment can just stay. And if you talk about encoding this using in a logical format, more specifically quantifier-free first-order logic over, say, the theory of linear integer arithmetic, you could have this formula. X prime denotes the next state, and x prime, the next state, could either be an increment, decrement, or stay. And for the environment, it's just state. Now, this con and n predicates induce a game graph. It's a bipartite graph as seen, and it models all plays. All plays are allowed by this con and n predicates. For example, more specifically, the controller states are shown in blue, environment player states are shown in red. Now, for example, this con predicate can use three moves. So starting from the controller, picking any circle state, I can either increment, decrement, or stay. And similarly for the environment, I could pick any state from the environment and just play the identity move. Now, a valid play of this game is as follows. You start from any state. You could start from the left, or you could start from the right. And let's say I start from the left, 2. Now you check what moves con allows you. 3 is allowed, you could play 3. From n view, you check what moves n allows you, and then you have this sequence of transitions. This is a valid play of the game that satisfies con and n. Now, coming to specifications. We care about specifications in the form of LTL-V formula. I'll come to that. What's it in a second? Basically, it allows us to specify what are the valid plays that we are interested in this game graph. So this is the syntax of LTL. I'll not get into detail, but keep in mind that it also consists of atomic constraints, which can be a formula of this form. Say x is between 1 and 3, assuming v is x. So this is an atomic constraint, and you could have temporal operators such as u, x, g, f. I'll not explain everything, but just a few. For example, g of psi means psi is true at every point in the given play. Let me motivate it with an example. For example, we could have a property that says the elevator always stays within 3 floors. This can be denoted by the LTL formula. G or x is between 1 and 3. right? So at every time step, at every point in the play, x should be between 1 and x should be between 1 and 3. And of course, this accepts this play here, but it rejects this play because 5 does not satisfy 5. Similarly, you have another formula which says something like eventually psi is true, right? Eventually, at some point, starting from the start state, some formula is true. And an example of that would be the property elevator eventually reaches floor 3. We can say denoted by f x equal to 3, and it accepts this formula because this play because 3 is reached here, and it doesn't matter after that what is there. And whereas here it's rejected because after a point it's only 1, but 3 is never reached. And an interesting property that we are also going to look at is all 3 floors of the elevator are visited infinitely often. Right. So what this tells me is 1, 2, and 3 must be visited at every point in time. It is never the case that exists a point from where either of them are not visited. Right. So, for example, if you look at this valid play 1, 2, 3 omega or 1, 2, 3 forever is accepted. But 1, 1, 1 is rejected because after this point 2 and 3 are never visited, right? So now you get a feel of LTL formulas, which allows you to specify the game or the valid place in the game. Now we come to the notion of a strategy. A strategy for the controller player, right? The ones in blue, maps all plays ending in a controller state to a non-empty subset of states. For example, this is a play starting from the state 2, but ending in a controller state 3, right? You can map, the strategy can tell me for this play, you can either choose the next state as 2 or 4. That's essentially what it means. So here I've in this play here, once I got this play 2, 3, 3, I've chosen 4. I could choose 2 as well. Next, a strategy is memoryless. If for all plays omega ws and w prime s, sigma of ws is equal to sigma of w prime s, which tells me that you take any path to come to the given state. For all such plays, you still give the same move. So you can just collapse the entire play to just one state. And essentially, you can say something like from state 1, just play 2, state 2, play 3. Sigma gives me the subset of states, right? The next move, right? The subset of states here. If the subset of states are equal for every play, essentially the next state. In our case, here we're calling the move as the next state in this context, right? From state 2, I could make the move going to state 2 or state 4. I think of this as a move for now. Yeah. So, right. So this is an memoryless strategy. Now, of course, you can think of these strategies as trees, but I won't get into that now. You can imagine them to be a tree starting from a given state. Next, right. So if you look at, so in this case, if you have a memoryless strategy, you can think of it as from 3, I'm just playing 2 and no other move, right? And from 2, I'm playing only 3 and so on. And this is how it looks like. Now, a strategy is winning from a state S in a logical game with the equivalent specification psi if all plays starting from S and which is according to the strategy, right? You play according to the strategy, and all such plays satisfy the specification. So that's what we call a strategy winning from a state S. For example, if you look at this formula, g of x always staying between 1 and x is between 1 and 3, this memoryless strategy suffices. Right? You start from 3, the controller plays 2, 2 brings you back to 2. I'm always staying between 2 and 3. Similarly, if I start from 1, it would be the same. From 0 and 4, we do not have a strategy. So it's not in the winning. It's not winning from, we don't have strategy winning from there. So this brings us to winning region. So states from where a winning strategy exists, right, exists for the controller player is called the winning region. So in this case, the winning region for the game is this shown in circle. And of course, you could have individual winning regions for the controller and environment player. Now, what's interesting to note is that for it's not the case that for every LTL formula that you will have a memoryless strategy. right? For example, consider this infinitely often case. And let's say from 2, I only choose to play 3. Like in the previous case, what would happen is I'm only staying within 2 and 3. And I'll never visit 1. So from 2, you need to keep track where you came from. If you came from 3, play 1. If you came from 1, play 3. So this is where you need extra memory. And in the sense, you cannot just collapse these 2 plays into 1. Right? From 1 to 2, you'll play 3. From 3 to 2, you'll play 1. You cannot collapse them. The strategies are different. So now that you know what is a memory strategy which is non-memoryless, every strategy can be represented finitely. In our case, using an automaton, it essentially captures what I just said. From 2, if I come to 3, I am coming from 3, play 1, and otherwise. Right? You can just verify that from C1. If x is greater than or equal to 2, then I decrement and then move to some state. If x is less than or equal to 2, I increment. The common states in these 2 states, C1 and C2, the common gain states are x equal to 2. So if x is equal to 2, I'm coming from one direction, I play one move, and vice versa. So this brings me to the problem statement. We have all the building blocks, and the problem statement is as follows. Given a game graph, which is modeled using a logical LTL game consisting of a game graph modeled using con and n predicates, and an LTL specification, the goal is to synthesize the winning region and the corresponding strategy automaton that comes with it. Which is, of course, easy to see that not really straightforward. How do you go about this transition? So that's the first question. Compute the winning region for a given logical LTL game, and if possible, also compute a finite memory strategy. The second question we are interested in is realizability. That given an initial region as well, decides the controller can win from all states in the initial region for a given logical LTL game. So how we go about solving such games are, so given a logical LTL game, say G, you first ask if it's a simple game. We'll come to what simple is in shortly. If the game is simple, solve it using simple techniques. Otherwise, solve it using not so simple techniques. And in our talks, what we're going to see, I'll spend more time on simple games and then give an overview of how to handle the non-simple case. So let's talk about this branch when the game is a simple game and what does that even mean. So simple games are logical LTL games where the LTLV formula is of one of these 4 forms, right? G of x, f of x, gf of x, or g of x. And keep in mind that x should not contain temporal operators. And for example, this is the LTL game with the formula g of g of x between 1 and 3 is a simple game. So let's see how do we go about solving such games. So we have the specification that every play, starting from a state, find the set of states from where every play. I have a strategy so that every play is staying within x between 1 and 3. So you can think of now I'll move to sets in the sense you can think of the set here denoted by this. Let's call it the safe set X that you're interested in. You want to stay in the sets 1, 2, and 3. Now, the first thing you do, I'm showing a diagram here for reference. This is how the fixed point computation works. And the left part, you can see in blue, the left half is the controller states. The right part, in this part, the red part is the environment states. Now I'll explain what this means. So first, what you're doing is you compute this set, which is WC0 as X, right? So what does WC0 mean? In this case, WC0 would become 1, 2, 3, as I'm denoting here, right? The set of controller states, which are having 1, 2, and 3. Now, what it means is that it is a set of states on which controller can start playing, first thing, and ensure that the play stays within X for at least 0 steps, right? We have not made any step here, and you are within 1, 2, 3. So it is satisfied. Right? And it's also denoted by this region here in blue, right? That's what we are looking at. Next, we compute the set of states, the WE1, right? Like the set of states from where environment can start playing, and still and a controller can ensure that the play stays within X for at least one step, right? And that's possible because the environment is antagonistic. We need to ensure that all moves of the environment fall within WC0, right? And that's only 3, 2, 1, because from 3 you have this going into W1, 2 also you have going into WC0, and 1 you have going into WC0, and you get a smaller set. I know you're not able to see a smaller set here, but in general, this is a shrinking computation for an arbitrary game. And what we do after this is similarly compute the set of states from where controller can start playing once again and ensure that play stays within X for at least 2 steps. So you get a sequence of sets in this form, and we terminate when WC of n plus 1 is equal to WC of n, and WE of n plus 1 is equal to WE of n. So this would become the winning region, W, right? I should have shown it here. The winning region is this 1, 2, 3, and 1, 2, 3. The key point to note is that starting from any state in W, the controller can ensure that it can keep the game in X for at least 0, 1, 2, 3, and hence always. So this is the winning region that we just computed. Then this computation may not always terminate. And from this winning region, you can extract the strategy, memoryless strategy, quite easily, right? So you have the winning region here. From here, you just cut off states that are going out of this. From 3, I will not play 4 because it's unsafe. Just stay within this region. So from 3, you're allowed to play 3 or 2. So now that we understood how simple games are computed, keep in mind that just a flash, all of this are not done concretely. We represent them symbolically using constraints, logical constraints, right? That's the key insight. And you can read the paper to know more about it. Right. So just an overview of all the simple games in our work. You can similarly compute Buki, co-Buki, reachability, and safety. It's a wide collection of fixed point algorithms that we have. And so this terminates simple games. And the idea was that, so we implemented safety in our first work, which was published in FSC 2021, which gave us, which was initially used in, ideas from it were used in the FRET tool by NASA Ames. And this gave us enough motivation to check out what if the games are not really simple. What about general LTL formulae? So in the case that the games are not simple, we have 2 approaches. I won't get into them in detail, but the key idea is that if you have, for example, this property here, which is not, really a simple game. The first thing you do is just convert it into a Buki automaton, which is a finite automaton with which accepts infinite words, infinite length words. But I won't get into details of this. You can go back to the paper. The key idea is that if it is deterministic, we go into the deterministic LTL game spot approach, which essentially takes the product of the automaton with the game and then solves the computation. And if it is non-deterministic, then we have an on-the-fly determinization approach, which is also known as a bounded determinization approach in the literature, which computes a sequence of deterministic automatons for a given bound and then takes a product and computes it. So these approaches are quite, you could check these approaches out in the paper, and we will move on to the experimental results. So what we are doing here is we compare with 2 tools back then. One is Consynth, which is a constrained horn clause based solver, which doesn't compute the exact winning regions. It requires external templates for the strategy. You cannot compute the strategy on its own for the problems that they consider. And for general LTL specification, that is games which are not simple, it's actually unsound. We found because it uses a non-deterministic Buki automaton to take the product, which is not really sound, and it doesn't scale well. Secondly, we look at the other tool, Rabonial, which is an abstraction-based dependent-based solver. Again, doesn't compute exact winning regions and doesn't scale well. And we show our results on these 2 tools. So we compare with Consynth, which is C. We have Rabonial, which is R, and Gensis, which is Gensis LTL. Now we have the specification. S stands for the specification, which could be G, GF. A non-simple game is what we denote by general, for example. This dash indicates that information not available. Timeout is set to 15 minutes. This here column is the maximum time taken across all the approaches. Simple, product, on the fly. And G of FA tells us which was the fastest approach that gave us that result. Right. So here you're computing the exact winning region first and the strategy associated with that. So if you look at star here, star tells us that the exact winning region is computed in this in each of these cases. Just to keep in mind, the on-the-fly approach that we have cannot compute the may not compute the exact winning region always. It can give you a controller that is sound, but it may not capture the entire winning region. This was a case which was a benchmark which we used to validate our was the first scalability result based on our approach, and we saw this in 45 seconds, whereas Rabonial times out and Constant does not have information for that. In the case of the elevator example, as we parameterize it with the floors 3 to 10, we can see that we scale well, and here in this case, Rabonial doesn't scale as much. This is an interesting case where Constant claims to solve it in 4.7 seconds. It's not a trivial example, and in this case, we solve it in 276 seconds. We are sound. The point to keep in mind is Constant on general LTL specifications is unsound because they use non-deterministic Buki automaton to take the product, which is known in the literature to be unsound, whereas we have determinization approaches to solve this problem. Similarly, you can see for other cases as well, we scale well. We perform much better than the literature existing tools in the literature back then. This shows in a different graph on how we are scaling as compared to, say, Rabonial. Right. So this brings us to the end of the first part of the thesis, which spoke about solving infinite-state reactive synthesis problem using logical LTL games. In the second part of the thesis,
How does it draw point algorithm?
right. So these are standard fixed point algorithms in the literature which were known in the finite state setting. We extend them for the infinite state setting, and more specifically, we have a constraint-based approach to solve this problem, which scales well based on certain tactics that we use in the algorithm. So these encodings that you see are essentially constraint-based or logical techniques that we use. Yes, what we look at is, for example, even the deterministic product LTL games. It's known in the literature that you can take a product and compute the solution, but compactly representing them using logical constraints is the key for scalability in our observation. And also, of course, we have these quantifier emission techniques under the hood, which helps us scale. And the on-the-fly determinization approach is also something which is novel in the sense that the bounded synthesis approach was known for the finite state setting. And here, how do you encode them using constraints in the infinite state setting was the key, right? So if you didn't have these constraints, you would have to explicitly determinize the Buki automaton for every value of k, and that's a very expensive process. We tried that. That's the first approach that we tried, and it blows up even for very low values of k, where k is equal to 1. And using such succinct representations with quantified elimination helped us scale for at least the first approaches to scale in these settings. So yes, the core idea is that although I showed a concrete algorithms in the concrete settings, we do not really use them concretely. They're all represented symbolically using logical constraints. And yeah, that's the key novelty here. So, right, is there any more questions in the first part of the thesis, or should I move on to the next? So we'll move on to the next part of the thesis, which is synthesizing, which is a resilient infinite state reactor synthesis problem. This is joint work with my colleagues at the Max Planck Institute for Software Systems. And here we talk about the notion of resilience, which is the quantitative property for the controller. So before I move on to resilience, I'll first talk about what games with disturbance edges are. The notion of resilience is antagonistic to the games that we consider. And in this setting, we'll use logical LTL games once again to motivate what is the notion of resilience. So what we do first is we introduce a new kind of edge in the logical LTL game. We call them disturbance edges that could arise from each environment state. As you can see, from 4, you have a normal edge and a disturbance edge. Why do you care about these disturbance edges, right? So these disturbance edges can be used to model environment uncertainties that may not always occur. For example, in the warehouse example, if the robot is not modeled or designed to take care of that liquid spill, that liquid spill could also be considered as, say, a disturbance edge, right? So what it means is, it's not always the case that you're going to have a liquid spill or a tornado, right? So it doesn't make sense to model such a strong antagonistic environment always. So the key idea is that if these disturbance edges are modeled as regular edges, right? Let's say one question you may ask is, of course, you have these disturbance edges here. Let's take each of the disturbance edges and make them solid. In this case, the environment can become too powerful, and it's either you may never have a winning strategy, or the winning region may be empty, or you could just have a very small winning region and say you can only win from these sets. On the other hand, if the disturbance edges are not modeled at all, like if these liquid spills are not modeled at all, then during such an event, the controller may not satisfy the winning condition, or in general, it could be hazardous for a human that's working in the field. So the question is, can we give a correct by construction strategy with respect to these regular edges of the environment, and a best effort solution in the case of disturbances? And this is what this is where I come into the notion of resilience. But before that, now you'll see that a play in this game is a combination of dashed edges for the environment and solid edges. It's as compared to the play in the earlier setting. So you have disturbance edges, and let's assume there's a function d of p that counts the number of disturbance edges in this play. So in this case, d of p is 1. Now we come to the notion of resilient strategies. There's a lot of text. I had added animations, but okay, let's focus on one at a time. So let alpha belong to this set, right? You have set natural numbers, you have omega or omega plus 1. Omega essentially means it contains all natural numbers. Omega plus 1 means that it contains natural numbers as well as omega. Now I'll come to the semantics of that in a second. But first to keep in mind is this important definition, which is a strategy. Sigma is alpha resilient from a state S in a logical LTL game with an LTL specification, say psi. If all play starting from S, which is according to sigma, and the disturbances seen in that play is strictly less than alpha, satisfies psi, right? So, for example, if I have a phi resilient strategy, it essentially means phi resilient strategy from a state S. It essentially means that it can tolerate at most 4 disturbance edges in that play. If you get the 5th one, you lose. Yeah, I see. Yeah, you're right. So it can tolerate up to 4, right? For sure. So you're guaranteed to satisfy the winning condition if you have at most 4 disturbance edges. And omega resilient strategy can tolerate a finite but unbounded number of disturbance edges. And an omega plus 1 resilient strategy can tolerate an infinite number of disturbance edges. That's the key idea here. And the notion of resilience are first spoken about by Snyder et al. In this work, synthesizing optimally resilient controllers. So alpha can be omega plus 1, right? Alpha is in this set, right? So I'm just explaining what alpha resilience means for different values of alpha, right? If alpha is 5, you can then you can tolerate at most 4, and so on. Now, once we know what an alpha resilient strategy is, we come to what is the resilience of a state. So the resilience of a state S in a game is R of S, we denote it by R of S, such that it's a supremum of alpha, such that there exists an alpha resilient strategy from S, right? From S, suppose there's a 1 resilient strategy that can, ensure that you can win the game under at most 0 disturbance, and you have an omega resilient strategy. Now, if you take a supremum of 1 and omega, you get omega resilience, right? So the resilience of that state will be omega if you have a 1 and say omega resilient strategy. Now, we say that strategy for a game is optimally resilient if it is RS resilient from every state in the game, every state S in the game. So I think there's a lot of definitions here. Let me try to explain this intuitively using and why these resilient strategies essentially generalizes the winning strategies that we saw in the first part of the thesis. So let's say I have this game without any disturbance edges, right? And I feed it into a standard solver, like the first part of the thesis. Let's say I solve it, I get a winning region, and I get a strategy. Since this winning region can win without any disturbances, right? Intuitively, it is intuitively from every state S in this winning region, you have a 1 resilient strategy, right? And you know for sure that each of these states have resilience at least 1, because it can tolerate at most 0 disturbances and still win the game. This is the case when you do an infinite state reaction system problem without any disturbance edges. On the other hand, if you model all the disturbance edges, right, as powerful entities, and you feed it into an infinite state reaction synthesis solver from the first part, and you get a winning region, either it would say, hey, it's unrealizable in the sense a winning region does not exist, or to give the most restricted region such that this region can win against any move, any possible, disturbances. It could be dashed as well as, solid. So these are essentially, these states are essentially omega plus 1 resilient because it can handle even infinite number of disturbance edges, right? Because we assume the most powerful environment and still these states are winning. Now, in the resilience infinite state reactive synthesis world, where we have disturbance edges, now we have a gradient, right? So, of course, it would still satisfy this condition and the one on the right in the sense of from the infinite state reactive synthesis setting. But also I can be more precise in the sense I can say from state 3, it is you can have a 2 resilient strategy. Or from state 5, you have a 5 resilient strategy, which is not possible with earlier techniques.
Stanley?
Yes. Hello.
I had a question on the rightmost figure.
Yeah.
From 2, I guess the circles are the controller states, right?
Circles are controller states, and 2 is the environment states. Yeah.
The circles are controller states, right?
Yeah.
So from 2, the outgoing edges are only to 3 and 1. So how would those twos form a winning region? Because in fact it does not stay
Right.
within
So
the
I
region.
mean, okay, this is I mean, I'm not, the underlying game is not precise in the sense it's not actually, it's just a dummy game. It's not really the exact states from where you can have a. I'm just showing you that in any given game, the key insight is that a game with disturbance edges, a game without disturbance edges, a game where disturbance edges are modeled as an antagonistically. I'm just showing the possible winning regions, how they can change. That's all. I'm not. They do not represent, the underlying game does not represent the exact setting. So yeah. So that's the key point here. So I think if you observe resilient infinite state reactive synthesis, where you have disturbance edges, you can have more richer strategies, which can say from state 3, play a move that is too resilient, right? Which will ensure that you can tolerate at most 1 disturbances. And for example, if you have an option between a strategy which is 2 resilient and 3 resilient, you could choose the one that is 3 resilient and say, hey, you can be tolerant more to disturbances, which is not possible in earlier techniques. That's the key insight or takeaway here. Right. So the problem statement is as follows in this setting: is given an infinite state disturbance game, right? A game with disturbance edges and a winning condition. Can you synthesize the winning region with resilience values of each state, right? So somehow you compute the resilience values of each state and also a resilience strategy, right? And the overall solution or the idea of this work is that in this, what we do here is we're the first to synthesize resilience strategies for the infinite state setting, right? Resilience strategy synthesis for finite state setting already existed. And we solve the infinite, compute resilience strategies for the infinite state setting using abstraction and refinement approach. What we do is we first abstract, you given a disturbance game, an infinite state game here, we first abstract the game, which is the graph and the winning condition, to a finite two-player game with winning condition over that finite game, and solve using resilient fixed point algorithms that compute the values of resilience for each state and synthesize the strategy. And finally, once you get a strategy in the finite state setting, right, you refine this strategy to get a strategy in the infinite state setting. And optimally resilience strategies exist for the finite state setting, which is proven by Daniel and others. However, it is not known whether optimal resilience strategies exist for the infinite state setting, or how can we even compute them, if at all. So we show, I'll show the results on a motivating example. So assume this, say, coming back to the robot example that we have. Think of this 2D map where you have obstacles in blue. You have spills on the floor, let's say. And the robot wants to reach this target shown in purple by avoiding obstacles. It could take the larger path, it could take the lesser path, for example. Now, let's say the disturbance edges come from, say, these spills, right? And we model it in the game and we try to solve the problem. So if you observe, without disturbance edges, this entire white region is winning, in the sense, from here I could play a move that could reach me to the target region and I'm still fine. And similarly, I could take the larger path, both are fine in the regular setting, which is solved, which there's a tool called Scots that solves it using abstraction-based control design paradigm. What we do is we use the techniques that I mentioned before, and we incorporate it into Scots. And we have our tool called Rescot, which is resilient, which does resilient ABCD. And what it does is as follows. As you can see, the case on the left is the one where you have lesser disturbance edges. On the right is the one where you have more disturbance edges. And as you have more disturbance edges on the right, you can see the gradient, right? You have exactly 4 resilience values for each state, right? Which is shown in dark pink, and you can see 1, 2, 3, and 4, right? And as you have fewer disturbance edges, you can have states that are more resilient to disturbance edges. And here you can see a more gradient with 16 resilience values. And the strategy that is generated for each of them does not choose the narrow path. That's the key insight here. Because in the narrow path, you have states with lower resilience. So it would not choose to move through a lower resilient state, because just in case a liquid spill or tornado comes, you are more, it's possible that you may hit the obstacles here, whereas here you have some more leeway. Now, similarly, another example is as follows, where you start from the bottom, say some corner. So here in this case also you have obstacles, and the resilience values are computed for a given disturbance value. You'll see that from if you're in a higher resilient state, you can move to any lower resilient state, it's fine. But if you're in a lower resilient state, you will not pass through the higher resilient state, right? In this case, you'll not pass through the higher resilient state, you'll still take the farther route. Yeah. The darker states are are the ones with a lower resilience value, right? So say 1 resilient. Here you're starting in a higher resilient value. Oh, this one, yeah, you're starting in a lower resilient value. Yeah. Right. So you could move to any. Right. So here it doesn't matter. You could move to any of the higher resilient states. It's fine. There is no problem. You could go here, you could go here. The controller would allow both. But here, if you see, if I select a state, the strategy tells me to move to this part here, which is lesser resilient, right? Than the one on the left.
The online people don't understand what you're pointing at.
Oh, okay. I see. So how can I solve this problem? Is this visible?
Yes.
Okay. I'll just explain this once again. So think of these grids where the resilience value is already computed for each state, where the darker resilience or the darker color denotes lower resilience values, and the lighter colors denote higher resilience values. And in the case, if the robot starts from a lower resilient state, I could move on to any higher resilient region, which is fine. So in this case, it just chose this target, which is the nearest. So that's what it would choose. But in general, it could even choose the left target. But the key point is that in this, if you start from a state which is already at a higher resilience value, it would not choose moving through a state which is, a low resilient value. Because of course, if you get a liquid spill or tornado or something, then you would, you may hit an obstacle here, but here you have a lot of leeway. So you see how resilience values for a state influence how what decisions are made by the strategy.
There are target positions, you can go to either one, is it?
Yeah, you can go to either one. This is the objective here. You could pick either one target, so left or right. So you choose based on where you start from. You choose moving through a lower or through a higher resilient. Yes, exactly.
Once it has seen some high disturbances, can't it then go through a horizontal detector?
Right, it doesn't know if you mean to say that you start and you see some n number of disturbances, and you know for sure that no more disturbances would come. But how do you know that how many disturbances would come? That is something which we do not have, right? So yeah. So these two examples motivate how resilient controllers are more make better decisions than a traditional controller that we saw in part 1 of the thesis. And right, so coming to future work, in infinite-state reactive synthesis, this is a fertile ground for a lot of work that can be done in the future, and this area has just begun. There are already many amazing tools. Yeah, these are the experimental results, actually. These two, where we show.
What is the takeaway?
So the takeaway is that the strategies synthesized using the resilient infinite-state reactive synthesis techniques can choose based on the resilient value of a state. They're more resilient than the previous ones, right? It has the opportunity to choose to move to a higher resilient state and avoid potential crashes or due to disturbances that are not modeled. So, whereas traditional techniques do not account for that, right? The key point to note here is that the traditional technique allows you to move through any of these two, but these two techniques do not allow you to take this path because you have a higher resilient path to take. That's the key insight here. So, right.
Are these colors actually showing the resilience of those regions?
Yes, it's showing the exact resilience of the regions, right? So in this case, so blue would be, of course, resilience 0 because they are obstacles, you cannot win from them. Here you have resilience 1, where resilience 2 here and 3, right? So you have 4 resilience. Yeah, of the control. The white one is synthesized using classical infinite-state reactive synthesis techniques. Let's say part 1 of the thesis.
The resilience of that controller.
Right. So here it is 1 resilient. If you talk about the winning region here, it's 1 resilient because even without any disturbance modeled, you're able to win from the region in white, which means that, of course, you can win the game with at most 0 disturbance.
You're saying that might actually be more resilient.
It could be more resilient. Yeah.
Any guarantee we can give is on.
Yes. In the first part of the thesis, you cannot give guarantee more than, say, 1 resilience. It could be more resilient, assuming disturbance, given the disturbance edge modeling. But this is all that a classical technique can do. Right. Whereas here,
they're not showing the actual resilience, but they're showing the guaranteed resilience.
yes, in both cases, the colors are yes.
So you are able to guarantee.
Yes. It may not be optimal in the sense because of the technique that we're using, the abstraction refinement based technique. Right. So yeah. So this brings me to the end almost where we have our future work for this domain. It's still a very fertile ground. There's a lot of work to be done. Scalability has to be tackled. For example, even further, even though we scale, we are not good enough for real world controller softwares, for example. It's still a initial research field, very nascent. You could improve scalability by, say, using composition algorithms for logical kill games, which is done by Rena's work to an extent, Rena's work as well. You could also have richer specification languages such as HyperLTL, MTL, CTL star. Completeness is another topic which has been tackled by Rena's group. And we could also use deterministic parity games to at least see if we can terminate, right? Instead of using a bounded determinization approach. They could use data-driven approaches to synthesize policies for such games, right? There already works on semantic learning being done in the literature. Of course, computing resilient controllers without an abstraction-based approach, that just using algorithms for resilience over logical LTL games is something we can try, assuming we have more benchmarks on the same. And so yes, so this brings me to the end. Just to give an overview of the contributions, we looked at 2 parts of the thesis, right? Where in the first part, we looked at infinite-state reactive synthesis using, say, logical LTL games, where you have a linear LTL specification. You have a reactive system, which is infinite state, modeled as a logical LTL game, all right, which includes a specification as well. And the tool Genesis LTL synthesizes the controller, which is correct by construction. And the property that, of course, the property that we look at is like scales. the best. It's actually the first tool that scales back then to a good level. In the second part, we looked at the notion of synthesizing resilient controllers for the infinite-state reactive systems problem. Do you have a reactive system and a temporal specification? It could be LTL, it could be parity, it could be anything. And here the key insight is that you have games with disturbance edges. These games could be logical LTL games. They could be any game in the literature. The notion of a game with disturbance edge is agnostic to the game underneath. And if the tool rescored synthesize a correct controller, which is correct by construction, but also more resilient than existing controllers techniques in the literature. And this brings me to the end of the talk, and thank you.
Congratulations, Dr. Stanley Samuel. Yes.
Thank you.
Congratulations.